Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Grind 75, a Better Blind 75 coding series. So today's problem is on cloning graph. It's pretty straightforward. Let's jump into the problem statement, understand it and start solving. So last time we have solved binary tree level order traversal. You can find it in the list. Let's start with clone graph. Okay. Let's understand the question. Given a reference of a node in a connected undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value, int, and list of its neighbors. So we can see value and neighbors, which is a list. Okay. Test case format. For simplicity, each node's value is the same as the node's index. One index. For example, the first node value is equal to 1, second node value is equal to 2. Okay, and so on. The graph is represented in the test case using an adjacency list. Okay, an adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. Okay, the given node will always be the first node, value 1. You must return a copy of the given node as a reference to the clone graph. Okay, so basically, as far as we would have understand by now, is we are given a graph, we have to just clone it and return the reference to the first node again. Okay, so for example, this is the original graph 1 2 3 4. We cannot return the same graph, that is not allowed. This looks like a clone, the nodes are new, graph looks the same. So we have to return a new graph which will have a clone of the original graph and then return it. We cannot return the same graph again. Okay, so we need a mechanism to find out that, okay, this is not the same duplicate but a clone of it, right? Third is we have to return them in the same order. So this one is not the same graph as the original one. Original one was 1 2 3 4. This is 1 3 2 4. Okay, if we see, we are given adjacency list, so you can see it is 2 4. That means 1 is connected to 2 and it is connected to 4. 1 3, that means 2 is connected to 1, it is connected to 3. 2 4, that means 3 or third node is connected to 2, it is connected to 4. And 1 3, 4 is connected to 1, 4 is connected to 3, since it is non-directional. Okay, so there are 4 nodes in the graph and output is also same, 2 4 1 3 2 4 1 3, as it was earlier, right? We just have to clone it. So we have to clone all the nodes of it and then we have to return the same node, which is the original node 1. So we have to return 1 from this one. Okay, so if you break this problem down into smaller things, one thing is we have to traverse through all the nodes, right? We can either use the breadth first search or the depth first search. We'll be going with depth first search so that we can use a method recursively, right? So we call 1, then we call all the neighbors of it, then we pick up the first neighbor, which is, let's say, 2, then we go to all the neighbors of 2, 3 gets picked up, then we go to all the neighbors of 3, 4 gets picked up, and then we return from 4 back because 1 is already picked up. We return back to 3, 2 was already picked up, we return back to 2, from 2 we return back to 1, from 1 4 has already been picked up, so the loop ends. Okay, so all we have to do is we have to traverse the graph. We'll use the DFS. We need something to clone and copy them, right? So we'll use a map, hash map. It's very easier to find out a copy because we can directly use the hash function. We can directly check if the node is already available in the graph or not, or sorry, already available in the map or not, right? Otherwise we clone it. So if a new node is not available in the map, we add it to the map, or else if it's already available in the map, that means the clone is available in the map. Okay, so let's start solving and maybe then we can understand it much better. Okay, so we'll do the first base check. If node is equal to null, right? If node is equal to null, we'll simply return null. That's it. Now we'll use a map. Okay, so use a map to keep track of nodes in the original original graph and their corresponding clones. So we'll create a map where we'll store the nodes from the original graph and a clone of that. Okay, so it will be simpler for us to find out if we have not traversed the original node, that means a clone of it does not exist either, right? So we'll create a hash map for this. We'll say map node clone map is equal to new hash map. Done. And we can actually call another method. Since we want to do the DFS, we want to call the method recursively. So we'll create another method. Okay, we'll call it private node clone node. Okay, node will pass the original and map node and clone map. That's it. So from here we can simply say return clone node and we'll pass the original node and our map, which is clone map. Okay, so since we have to return the final node, which is 1, we'll directly call another method clone node, which will be returning us a node and return that as our solution from this clone graph method. We'll pass the original node, which is this first node. We'll pass the clone map, which is this map, which is blank as of now. So we have the original node as original and the clone map. Now we're at the first one, so let's start it. Okay, so what will we do first is we'll check in the hash map if this clone already exists or not, right? So check if the node is already cloned, because if it exists in the map, that means we have cloned it. So we'll check if clone map dot contains key, okay, original. So if it already exists, that means we can we have already added this original node, that is 1 for the first case, to the clone map. So let's return from this. Okay, you can say return and return clone map dot get original. Now why clone map dot get original? Because we are storing in the map node and node. So the first node is the original node, this one. The next node would be the clone of this one, which we'll be creating. So if the nodes have already been created, we'll simply return the clone of it. So we are saying clone map dot get and we are getting the value for the original node. Value for the original node is the clone node. We'll understand it from the else example. So if it is not contained in the map already, okay, that means now we have to clone it. So clone the current node. How will we clone? We'll create a node, let's call it clone is equal to new node. How do we clone it? We will just create a new node and pass the value 1, right? Where is the value 1 right now? Value 1 is in original. Since map does not contain it, right? 1 was never added to the clone map, so this method will be false. Loop will not enter this line of code. So we'll create a clone new node and we'll pass the value from original dot val, right? Oops. Okay, so now we have created a node named clone. So now we have a node, let's add it to the map. We can say okay, clone map name is clone map dot put. First node would be our original node, this one. So we'll say original and second would be clone of it. That's it. That is actually all the logic that we need to know. Now all we have to do is we have to call the same method recursively on its neighbors, right? Since we are performing the DFS will directly call on this neighbors, and then from this neighbors to the neighbors to the neighbors, right? So we'll say recursively clone the neighbors. Okay, so we'll say for, we are going to call it on all the neighbors of our current original node, which is 1. So for node neighbor original dot neighbors. Okay, and we'll say clone. So what is clone? Clone is this method. Now this is also a node, right? So this we created a new clone, but this is also a node, so we need the neighbors for this node also. Only then the whole clone map will be connected, right? So that's why we'll say clone dot neighbors dot add. So they have their neighbors list as well, right? Clone dot neighbors dot add, and now I will add the list of nodes that will be returned from the DFS to the first original node. So I can call the same method again, clone node. We'll pass the original method, so original node right now would be neighbor. So sorry, this is neighbor. So we'll pass IGHBOUR neighbor and clone map. Clone map is our overall map which is controlling everything. And when everything ends, we can simply say return clone, right? So what happens is, let's go through it once, dry run. Okay, we get 1, we call original node as 1, we create a blank clone map. Okay, let's take clone map here. Oops. Okay, right now it's blank. Our current node is 1. We check if it is available in the map. It is not. So we create a clone, right? We create a clone node and we pass the value original dot value. So 1 is passed. So this clone node is created, just the node, not the graph. Now we put this in the into the original map. So 1 is inserted into the map. But right now 1 is not associated with 2, 3, 4, anything. Then we recursively clone the neighbors of our current node, right? We check for the originals member. So originals member is 2. So let's say we next call the we call the clone node on 2. Okay, so neighbor will now be 2 and clone map is the same clone map. This method gets called up. Does the clone map contain 2? No. So we create a new clone node that is created from 2's value. 2's value it has been created. They are still not attached. Okay, and then we add them to the clone map. So in clone map we have added 2. But now each of these node have their neighbors list, right? They have their neighbors list, but that has not been edited as of now. So 1 is there, 2 is there. Now we check for 2. We check for the neighbors of 2. Okay, now the first neighbor of 2 gets called. Let's say 1 gets called. We check here, we call the clone node. Original node would be 1 now. We check the map contains this node. Yes, map contains this node. So let's return the clone of it. So 1 gets returned from the here. So in clone neighbors, so on this clone 2, in its neighbors list, 1 gets added to it. So now we know 2 is attached with 1. Okay, let's create the attachment like this. Similarly, the next neighbor gets called, which is 3. So for 3, we again call the clone node. Clone node checks if 3 is a part of the map. No, right? So 3 is added to the map. Now for 3 again, we created a clone. 3 is created, but it is not attached. We call for the neighbors. Okay, now I will go a little faster since everyone must have understood by now. So for 3, it checks for the neighbors. It can check 4 first or it can check 2 first. It's checking from the original neighbor. So we'll check for the neighbor. Let's say we check for 2. We check it. Is it part of the map? Yes, it is part of the map. Let's return a clone of it. Clone dot get original. Okay, so we are returning the value, which is the clone. Value is this part. So 2 gets returned for 3, and that gets added to 3's neighboring list. So 3 is now attached to 2. Now next neighbor was 4. 4 gets called. Is 4 already contained in the map? No. So 4 gets added to the map. Now we call for the neighbor of 4. First we call the neighbor 1. 1 is already in the map. Yes, 1 is in the map. So we return the clone of the 1, right? And then we add it to the neighbor in the 4's list. So 4 will get attached to 1, right? The next neighbor of 4 is called, because recursively we are in the last node 4. So next neighbor would be 3. 3 is part of the map. Yes. So 4 gets attached to 3. So 4 now was already attached to 1. 4 also gets attached to 3. Now call for this node is over, and this is returned back to 3. Now what is written back 3? The node which was clone. Since for 4 it was all completed, the clone, that is 4, became the final node. It gets back returned to 3. So for 3, new neighbor gets added here, and that is 3 pointing to 4. Similarly, the same will happen for 2. Now 2 will get attached to 3, and then finally 1 will get attached to 2, then 1 will get attached to 4. This way the whole graph will be reconstructed inside the map. Okay, yeah, so let's run it and let's check. I know the problem was a bit complicated, but if you pay attention, if you go through the video a little slower, it is much simpler problem and will make a lot of sense. And this will clear out a lot of frequently asked questions on graph and DFS for yourself as well. Okay, we are getting some error here. Cannot find the symbol original. Okay, anything else? Original dot neighbors, cannot find the symbol neighbors. NEIGHBOURS, which line is it? 43. NEIGHBOUR, neighbor. What's the spelling of neighbor here? It's the American neighbor. I'm using the British neighbor. Okay, so let's change it. Neighbor, neighbors, 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 remove S, remove S. Okay, let's run. Great, let's submit and check. Okay, beats 45.96% of the users. I thought the time complexity was much better. Let's submit it again. Did I miss something? Beats 96% of the users. Okay, yeah, so that's all from today's video, everyone. Okay, but please rewind through the video. Please pay close attention to this. A lot of problems based upon these questions are very frequently asked in the interviews. Okay, so that's all from today's videos. For anything, please let me know in the comment section. Please like, share and subscribe. Thank you.